Você sabe como acender o ar-condicionado?
Aqui, ó. Nice. Só subir aqui esse lado.
So if he gets Fernando,
Sure, yeah.
So if he gets to hold this.
No, it's fine.
So good afternoon, everybody. Welcome to the second day of the Minicourse. This is the first section, again by Fernando. Please don't forget that after the immediately after his talk, we have the group picture. So stay around, right? Because the picture is going to take place here before the coffee break, right? So try to stay around until the others come. Anyway, thank you.
All right. Well, hi, everyone. So, is there any question from last time? Did you try to do the stuff that I suggested? No? Yes? Could you do it? Or? Okay. So what we did last time was composition, right? And what I want to do is just to continue on entanglement, but to give you an operational definition of entanglement. And then we'll go to quantify entanglement, at least for pure states, which is simpler. Then I want to discuss just a little bit mixed states. And then we go to some applications, right, which I think will be interesting. So this class probably is just quantum information theory again, and some applications already. So what we're going to see today, we're going to apply it to understand like information in black holes and to understand like work in thermodynamics and some things in quantum chaos. So it will be a very useful tool, but let's first see the abstract theory in quantum information. So I want to start with this. With like what we call local operations and classical communication paradigm, and that's the way in which entanglement emerged very naturally, right, operationally. So what is the idea? The idea is that we have, for example, can be more, but suppose we have at least two experimentalists, Alice and Bob, but they are very far away from each other. You cannot send quantum particles from. Maybe they don't have optical fiber, or this optical fiber is very noisy. So if they send some photon there, you decohere, and then it's just some classical communication. So they can do whatever quantum mechanics allow locally, right? They can do unitaries, they can add ancillas, they can do measurements. The same for Bob, but they can only communicate classically. There is a communication between them, but they can only send classical bits, right? So it's classical communications. Right, so basically what we're doing, we're putting a restriction on the type of physical operations that they can implement, right? This is what we're doing. And, okay, so what is a particular LOCC operation? Alice can make measurements, right? Okay, she can do a unitary, then make a measurement. She gets some outcome, communicates the outcome to Bob. Bob, using this information, makes some unitary and another measurement, communicates back to Alice, back and forth, right? And they can keep doing that as many times as they want. Right, so this is basically just saying that's the class of operations they have access to, LOCC, if class communication is cheap, but quantum communication is expensive, right, which is our world nowadays. At the moment, it's an interesting restriction. And then you can ask, so you can ask many questions, we will ask them, but question one, which states we can create by LOCC, right? And what I mean create, well, suppose Alice and Bob just start in a completely uncorrelated state, right? So suppose Alice initial state is 0, and Bob initial state is 0, right? For some element of the computational basis, just some pure states that have no correlation. And now suppose we want to apply, right? So in the end, they share state rho AB, which is lambda applied to this 0 state, where this lambda is any LCC operation you want, right? Another question is, what is this class of states, right? In class of states, they are what we call separable states. They are just a lot of product states we saw before, but now for density matrices, and because of that, we are there. So we say, so what is the definition? Rho AB belongs to separable, is a separable state. If we can find a convex probability distribution and some local states on A and some local states on B, such that rho AB can be written like that. Or actually, this is also true, but just to make the connection easier with product states, let's do this pure. Okay, so what is it saying? This is saying that, okay, we have like 4, right? These were our unentangled states. We allow some classical mixture here, right? So there is some classical lack of knowledge about which of the product states we have. Is that this is the case, right? So rho can be created by LCC if and only if rho AB is separable. Okay, so this is the set of states that you can create, right? By just coordinating classically any way you want, but without sending any quantum particles, right? But now there are states which don't have this, right? So there are states which are not separable, and those are exactly the states that we entangled. Okay, so rho AB is entangled. So if you want the operational way of defining entanglement is just the set of quantum states which cannot be created by local operations and classical communication. And then you see that there must be some correlations beyond to what we can have classically, right? Because here we can create as much classical correlations as we want, right? We can just communicate classically any amount we want, right? So that's a way of distinguishing the truly quantum correlations, then like the entanglement from classical correlations. Is this clear? Any question? Okay. Good. So, okay, why that's the case, right? Why this follows? It's not too complicated, right? So first, suppose let's show that if a state has this form, if it's a separable state, you can always create it out of some uncorrelated state, the 0,0 state by LCC. What they do? Well, Alice just samples from this probability distribution, right? It has a random variable given by this probability distribution. Then she samples, and she gets outcome k. Then she communicates this outcome to Bob. And then Alice prepares locally the state psi ak, and Bob prepares the state psi bk, right? And then what is the mixed state that this process prepares? Exactly rho AB, right? So that's easy, right? And moreover, right, you see that they don't even need communication, right? They only classical share randomness will be enough, right? But with classical communication, this can be done, definitely. The other way is a little bit more subtle, but you just so let's just break LCC into what is its components, right? So what is a LCC? LCC, Well, first, it's a very complicated class. We don't have a nice characterization of it. And exactly because of this ping pong that goes on, right? So, Alice can make a measurement, and then Bob makes a measurement condition. That, for example, for infinitely long time to achieve like maybe some probability of some conversion, right? So it's a complicated class, but nonetheless we can break into LCCs like yes.
As Alice communicates to Bob, in this time the state of Alice evolves in time.
Well, no, we assume that she can control her quantum system the way she wants, right? So she can stop the Hamiltonian, for example, right? So is this view where
So we can maintain the state in an eigenstate which is stationary.
yeah, there is no decoherence, that's right, and moreover there is no dynamics if she doesn't want to. So at her by any unitary she wants, but just switches off, right? And she can make any measurement she wants. So locally we allowed anything in quantum mechanics, right? We can do in quantum mechanics, but the only restriction is like locality on the quantum operations they can implement. Right, so the composition of what? Of local unitaries, local measurements, and classical communication, right? And now I'll leave to you, okay, the first thing you should do today, like exercise, to check that if you start from a state of this form, a separable state, and you do a local unitaries, again it has this form, right, that's pretty easy. Second, that you start from separable state and you make a local measurement, then it has this form as well, that's also easy. And finally the class communication doesn't change this class, so that's a little bit more complicated, but I'll leave to you to think. We can discuss the beginning of next class in case you get stuck. But try just to show that, okay? That because you can compose LCC in these building blocks, and each of the building blocks preserve the set, right? Then, the composition, even though there might be this composition with infinitely many rounds, has to preserve it as well, right? Yes?
We don't require that to be a basis, right? I mean,
No, that's right. Good point. Yeah, right. Okay, indeed. So they do not have to be orthogonal. Yeah, yes. They can be any states. Right? Okay. Good. So now with this, right? Okay. So this is nice because it's to define entanglement in a more operational way, but there is more. So if this setting of LOCC is relevant for us, right? And many times it is, exactly because it's hard to communicate send quantum particles over long distance without having the coherence and so on, then entanglement becomes a resource, right? So that's the view that appears many times in quantum information science, but here we can already see an instance. Is the view that entanglement is a resource, is something, it's some physical quantity that we can use to do stuff. It's the same maybe as like energy, right? We use it and then we can do something that we couldn't do without it. And how this manifests here, in the sense that, let's show now that if you have LOCC, this restriction on the quantum operations, and we have entanglements, so we allow ourselves, so Alice and Bob initially, they can share some arbitrary entangled states, okay? And we're going to see what is the right one. Then, in this way, it is the same as the set of all quantum operations, right? So we have a restriction on quantum operations, but if we add entanglement to it, then entanglement allows us to implement any quantum operation now, right? So that's the way, that's a sense in which is acting as a resource here. Okay. So who knows how to do it, how to show this? Who has an idea? If you've seen this before? Who has heard of quantum before? Okay, not few. Right. So that's because of quantum teleportation, right? So let's see how it works. Maybe I use this one. Okay, so let's put this statement that on hold for just a little bit, and let's just look at quantum, and then we see how to it directly follows from quantum teleportation. So the name is great, right? So unfortunately, it's a bit underwhelming once you see what it actually is, but it's pretty cool. But because of the name, right, it's a bit it could be better. So what is this idea? This idea in words is that if Alice and Bob they share the right entangled state, in particular, for example, then by communicating 2 bits of classical communication from Alice to Bob, Alice can teleport the quantum state of a particle that she has to Bob. Okay, so it is in a sense like teleportation that we see in sci-fi, but only of the quantum states, right? Not of like the particle itself. But if all the particles are indistinguishable, right, apart from the quantum states, or we can think so. So this is almost as good as that. So in more detail, imagine they have Alice again. We have Bob. They share an initial entangled states. This will be, I'll do teleportation for a qubits now, but it works more generally. So this will be the state that we saw before last time, right? This guy is just a 2-qubit maximally entangled state. So they share this state. This one, let's call A and B. Okay. Let's label the two halves of this maximally entangled state by A and B. But Alice also has another quantum system. Okay. Let's call it A prime. And this particle is in some quantum state psi initially. Okay. So what is the total states? Alice has this A prime register. She also has half of a maximally entangled states, and Bob has the other half, right? So that's the initial state share. Okay. Note this is completely independent of psi, right? And now I'm going to show you how Alice can make. She will make a joint measurement here. Okay. So Alice measures here. It will be a measurement with 4 outcomes. Then she communicates the outcome to Bob. Then given the outcome to her half of the maximum entangled states. And in the end, the state psi now here on Bob. Okay? And this initial prime in some state that we're going to see what it is, which is completely independent of psi. Okay, so it's just a way of psi, the quantum state here goes from here to here, from Alice to Bob, right? And that's, in a sense, is remarkable, right? Because this the only communication that has from Alice to Bob is 2 bits of. But note that if you to specify this quantum state, you need, right, to specify it exactly, you need infinite number of bits, right? It's like this wave function, you have to specify these 2 complex coefficients to arbitrary precision, right? But because you think about quantum mechanics, this will work, right? And that's the point of so let me tell you how to do it, and then I'll tell you a little bit more of the implications. So what is the protocol? Step 1, Alice measures the system A, right? She has, right, both A prime and A in what we call Bell basis. And this Bell basis is just is a projective measurement, right? With with 4 rank 1 projectors, phi plus minus and psi plus minus, and they are just the Bell states. So this you already saw, right? So you can just put a minus here and write this. Psi is very similar, but now, right, it's just some definition. Now it's okay. So you can check that they form a resolution of the activity, right? So if you sum these 4 projectors, you get identity. That's easy to check. So they are right. They are quantum measurements. So Alice can do that. So Alice implements these measurements. Then Alice sends the outcome to Bob. Right, so it's a measurement with 4 outcomes. So you need 2 bits to specify the outcomes. So these are the 2 bits which are sent, right? And finally, sends outcome, and we are going to label this outcome by these 2 bits. Okay, so let me call them ij. I'll tell you how to. Right, these 2 are bits. So ij, where I is a bit, j is a bit. I'm going to tell you how we specify I and j depending on which one we got, right? And then Alice will apply our unitary. We apply a unitary which is one of the Pauli matrices. Okay, so she will do X is a Pauli X matrix, Z is a Pauli Z matrix to the power of ij. Okay. So for example, if the bits are 0, 0, she does nothing. If the bit is 1, 0, 1 and 0, she applies X. If it's 0 and 1, she applies Z. If it's 1, 1, she applies X times Z. Okay, and now claim final states will be this guy on A prime. That's the final state. Okay, so we have state on A prime, which is actually know where it is, identity tensor xi zj, and this maximum entangled state. So completely independent of psi, and we have the state psi on B. Okay, so it actually what we want, right? Sorry, the quantum information which was stored in A prime originally, now it's in B, right? And the only thing that they communicated was this 2 bits of class communication, and they used the entanglement, right? Note that before there was entanglement between A and B. Okay, this is destroyed, right? So now there is still some entanglement between A and A prime, but this doesn't matter, right? Because Alice has A and A prime, so she could create this for free, for example, right? So this state is not very relevant. Any question here? Is this clear? Yes. Yeah, they are the Pauli matrices. No, Pauli matrices. So they're unitaries, right? They're both emission operators and unitaries, right? But in that case, we're using that they're unitaries. So they are those, right? Any other question? Yes. Yeah, Bob. Oh, sorry. Yeah, thank you. I was wrong here, right? Yeah, thank you. Yeah, of course. Bob has up, right? Bob has up, right? Yeah, and then that's the state, right? If Bob didn't apply this, then this xz would be here, xizj would be here as well. Okay, so I will not prove to you this in detail. I will ask you to work out the details, but I'll just tell you the idea how this is done. I mean, it's kind of it's a direct computation in the end, right? So suppose let's analyze the case where the outcome is 0, 0, for example. Then if the outcome is 0, you just project this onto 5 plus, right, on A prime A, right? Then, if I j equals 0, 0, then what you're doing is you have this state 5 plus on A prime. We do nothing to B, of course, right? And we apply that to psi A prime to this guy, right? But now, what you can do, you just write this in a product, in some product basis, right? You just write psi A prime as alpha 0 plus beta 1. Okay? And then this is a computation you can do, right? So we know how to write this explicit in the basis. We know this as well, right? This is 0, 0 plus 1, 1. You just do this computation. And then you see that this is equal to Lemme-Finding normalization will be half times phi plus A plus and psi on B. Okay? So it's just like you do this computation, you see that. Now you can do the same computation when you have the other Pauli matrices, the other Bell states, these guys. And then you see something very similar, but instead of nothing here, you have one of the unitaries apply here, either x or z or x times z, right? And then, you know, that basically it's, right? So if Bob can undo this unitary that was applied there, he's in good shape, right? So that's it's really worth to do it at least once, right, to understand this. But the calculation is very simple, right? One thing that might help you, but you should also work it out, is that actually all these states, these Bell states, all related to one another by a local unitary in one of the systems. So phi minus, for example, you can write as phi plus times z, right, applied to one of the qubits. And the same thing for psi, right? They can all be obtained one from the other by applying locally either x or z, right? And then this you try to use that too. Okay. Now going back, right? So teleportation, now I'll use it as a given, right? That we already know it. And now we want to show that if you just have this restricted class of operations and we have entanglements, and now let's be more specific. Suppose we have LOCC and we have a bunch of these phi plus states, right? So we have many copies of it for, you know, n sufficiently large, then that's equal to all. Then we can implement any operation that we want, right? And what is the idea now? Well, just suppose that we have Alice and Bob again. They initially are in some quantum state. It can be anything. It can be some sigma AB. And they would like to implement some quantum operation lambda there, right? The quantum operation lambda, which maps density matrices on HAB to density matrix on, for example, A prime, B prime. But now because this is not LCC, is not clear, right? They could not do that by LCC as well. But now, in addition to that, right, as is here, they have many copies of this EPR pair, right? This is also called EPR pair. They have many names, right? It's like a Bell state, one of the Bell states. It's called EPR pair. It's called maximally entangled states. So all of those are in phi plus. Okay. So they have all these states. And now what we can do? So who has an idea how to prove this now using teleportation? No, sigma AB is so the goal. Yeah, let me clarify. Goal. Apply lambda to sigma AB. Right, this sigma AB is stated they have there initially, and they would like to apply this quantum operation there, right? But this is like a general quantum operation. There is no locality restriction, right? And now the idea is how to do it using these entanglements. You can use for free this entanglement. You can use as many EPR pairs as you want, right? And you can use classical communication as well. Any guess? So what do you do? You know, this can be a state, a big state, right? But you can decompose in terms of qubits, and let's write in terms of qubits, right? Suppose it has n qubits on Alice, n qubits on Bob, the states, right? For instance. Then what they will do, Alice, using this resource, will teleport each one of the qubits, A1, A2, AN, to Bob first, right? So, what here I can do, right? So initially they had A1, AN, B1, BN, Then by teleportation, Ellie sends, well, let me do that. Ellie sends each one of her qubits, the A, by teleportation to Bob. Right? And then in the end, what this happens? Well, in the end, Bob now has the whole state sigma, right? So the A part has been transmitted to Bob. He has the state sigma, but now it's a local state on Bob. He can do whatever he wants, right? So he can apply this quantum operation. Then Bob locally applies this, okay? So now Bob locally has lambda sigma, and now he teleports back to Alice, right? He teleports now the A part of lambda sigma back to Bob, to Alice, right? And this achieves this, right? So it's just teleportation back and forth, right? So is that clear? Okay, think about it. If it's not too clear, try to write more explicit, but you see it works. Right, that's the, sorry, yes? Okay, so if you wanna, sometimes it's written like, what teleportation is doing is that you have, so this is called like a E-bit, you know, this 2-qubit maximum entangled state, because it's 1 unit of entanglement, right? E-bits plus 2 classical bits, C-bits. That's stronger, that simulates 1 qubit. Right, so what this says is teleportation, basically, right? So using 1 bit of E-bits of entanglement, 2 bits of class communication, you can transmit 1 qubit, right? This is what it's saying, right? And this is what we use here. Okay, yes?
What spaces are A, B, and A prime, B prime? This is the difference from A to A prime.
No, this just, you can assume they're the same. I'm just saying it's a quantum operation, so you can change the output Hilbert space, right? You could add an ancilla, or you could trace out something, right? That's why it's different, but for simplicity, you can assume it's the same too. That doesn't. You cannot. No. It is. You use the entanglement. If you want to recover the entanglement back, you cannot, right? Yeah. Oh, because we use right. So to go back, to go forward, we use n pairs of these maximum entangled states, right? So we use n copies of this maximum entangled state, and then to go back again, we have to use another n pairs. So in the end, we use 2n copies of this guy, right? It's not that we undo the physical process. It's just that we do teleportation, but now in the other direction, using fresh pairs, right? Yeah. Okay. Right. So now, teleportation is also nice because it gives us a motivation to start quantifying entanglement, right? So suppose now that say, okay, our goal is to do teleportation. We want to do teleportation. If we have this states, this EPR pair or this maximum entangled state, we can do it perfectly. But suppose now we have some other state, right? So suppose, you know, some other state sigma rho AB. And if you just try to do the same protocol using these states, you see that you get some noisy version of teleportation. So it doesn't really work perfectly, right? So, you know, if this rho AB is very pair, it will work pretty well, but actually it degrades, right? And for many of them, doesn't work at all, even if it's entangled. So okay, that's the problem, right? So, but now suppose we can do something more. Suppose 1 copy of rho might not be enough, but we can ask another question, which is, can we use now, right? So this like this noisy version of entanglement might not be directly useful, but maybe we can use many copies of it and do some more elaborate protocol, right? And then teleportation again. Right, so that's also a question that we might be interested. And this leads directly to an important concept in quantum information, which is entanglement distillation, which I want to tell you now. Okay, so what is entanglement distillation? This is the task of getting entanglement out of a noisy entangled state, but many copies of it, into a very good form, namely this EPR pair, but potentially with a fewer number of copies, right? So we want to concentrate the entanglement into a good form. So the task is that to start from row AB, right? Large number of copies. You just imagine we have an experiment generating row AB, and we repeat over and over again, right? Yeah, and then we like to apply LUCC, which is what we have access to, and get maybe copy, right? Or maybe some other number of copies of the maximum entangled states. Okay? And then once we do that, then we can use this for teleportation, right? To teleport m qubits, and this will work perfectly, right? So what is, I don't know, what is one set in mind? So suppose these guys, right? Suppose Alice and Bob, they want to communicate, but they are far away. Then they initially prepare, they initially Alice maximum entangled states, but sends the B part through this noisy channel. But then because there is a noise, in the end, this creates a state rho B between them, right? So that's one way to have in mind, right? Some experimental setting when this happens. And then they can send another particle through the same channel again, right? And they can do them many times. In the end, they have all these copies of this noisy rho B. Now, and that's sometimes a problem, but assume that they have a quantum memory, right, where they could store this without a lot of error. Then they have all these states, and they want to purify by what they can do, which is this local operation class communication, to the good form again, right? And once they have the good form, they can do teleportation. I haven't told you yet, but they could do key distribution. They can do many things, right? So this is like the problem. People think about this. This setting that I said is like the name of quantum repeaters. Is this idea of trying to establish entanglement over very long distances, and for that you need some kind of entanglement distillation, right? So that's something people implement eventually. There is experiments with when you have like 2 or 3 copies of rho B, 2 qubits, and you distill it. But of course, to do it in a scalable way, we are not there yet, right? Okay, so what do we know about this, right? About this problem? One nice thing about this problem is that then we can start studying entanglement in some quantitative way, right? We can ask, okay, how good is this rho B with respect to a APR pair, right? So how much worse it is than an APR pair? In other words, what is the best, right, for a given n? What is the highest that we can get here, right? So what is the best way, the optimal way of doing this entanglement distillation, right? There's these questions, and in general they might be difficult to answer, but for some particular cases, for example, for pure bipartite states, they have a very nice answer, which I want to tell you. But before that, I need to tell you some more math. So the way I describe this, there's some, in the end you get perfectly m EPR pairs, right? But there is no reason why you need m perfectly EPR pairs. Maybe it's just a state which is close enough to this one, you are happy. So we are going to allow that, right? So we are going just to get an approximation of, m EPR pairs. But what does this mean, right? I haven't told you yet, right? So how we quantify how close these quantum states are? I'll tell you this now. So let's use trace distance. So first, given a matrix, this is just some matrix X, the one norm, the Schatten one norm, for example, you define this as just trace square root x dagger x. Okay, it's just a matrix norm. And now we can compute this norm for 2 quantum states. So suppose these are density matrices now. And now there is this expression, which is good for computations, but is not so illuminating, right? But what you can show is the following. You can show that this, when rho minus sigma is actually like traceless, is the case because they are quantum states, that this is the same as 2 times maximum over some matrix M, for which all eigenvalues are smaller than 1 and bigger than 0, of trace M rho minus sigma, maybe absolute value. Okay? So there is this expression. And this is very nice because this gives operational meaning to this, right? What this says that suppose you have a game where you don't know if you have rho or sigma, you have one of the two, but you prepare one of the two in the lab, you have these problems, but you have no idea which one. And now you want to make a measurement to distinguish, right? Now because there is only possibilities, this measurement is enough to have a measurement with two outcomes, right? And then what you do, you just do, for this task, you want to do a POVM with two outcomes, which always has the form, right? M and identity minus M. Right, where M is between 0 and 1 as an operator. Identify. So, the most general measurement in quantum mechanics is a POVM, which has exactly this form for two outcomes. So who doesn't know what is a POVM? Raise your hands. Good. So most of you know. So yeah, just accept this, that the most general measurement in quantum mechanics has this form, and I can tell you in the end of the class, because I don't want to introduce them now. Yes. Yeah, it's the trace of the square root that's important. Yes. Oh, just the way, right? So for a Hermitian matrix Z, any matrix function, right, you define in normal way. So you just decompose this, right, into eigendecomposition, right, and we apply the function to the eigenvalues, right. So. But now because, right, system definite because it's x dagger x, right? So you can take the square root, right? So that's so what is this? So the trace norm is just twice the bias that you get making the best measurement, because you maximize allowed by quantum mechanics to try to distinguish rho and sigma. So in particular, if the trace distance is like epsilon, is very small, the two states, any measurement that you make on the two states, they can differ by at most epsilon, right? So if epsilon is very small, for all that we care about, the two states are the same, really, right? So once you quantify this error norm, okay, we want trace norm to m copies of API pair, and we want the accuracy, the error of the trace norm to goes to 0 when the number of copies grow. Okay, so that's the and many times we are going to consider, in the other lectures we are going to consider similar things. There will be always errors involved. You can always have the trace norm in mind. This variation. Sorry? Subscript is a 1, yeah. Because this, right, so well, this is a side, you don't need that, but you can define with a P as well, which then will be this function of the matrix, okay? But we are not, yeah, that's right, yeah, exactly. So these are called Schatten P norms. So that's the reason for the name 1 there. So when P is 1, you get exactly this expression, okay? But they are also used in quantum information, actually. They are used a lot, but in this class, we are not going to use them. Yes?
So when you talk about distillation, you want to maintain like the same systems. Like you want to distill a maximally entangled pair on the same systems.
Well, not really, because we allow LCC, right? We allow LCC, so we can bring some ancillas, we can trace out stuff, right?
So you can be like a maximally entangled state of A prime.
Oh, right. Oh, I see. Yeah, the good point. To be really, yeah. A prime doesn't have to be the same. That's right. So okay, so for pure states, bipartite pure states, I'm going to show you what we can do here and what. Okay, so that's a nice result. But let me see in time. But just that you gain some intuition, let me just give you an example of distillation. So, a very simple one. Suppose this rho AB is a state of a qubit and a Q-treat, okay? And it has this following form. With some probability P, or even let's put probability half, you have the maximum entangled states of 2 qubits, okay? So this, right, it's a maximum entangled state of 2 qubits, meaning that, right, so the basis here is like 0, 1, and the basis here, let's call 0, 1, and 2. This is a maximum entangled state of this with the subspace 0 and 1. And with probability half, Alice has the maximum mixed states, for example, and Bob has the 2 states. Okay, so that's their quantum state. And now they would like to do teleportation with this, right? But it's not clear, they cannot use it directly, it wouldn't be good. But there's a very simple distillation protocol that they can do here. Namely, Bob, they have many copies of rho AB, right? And what they do is, in each copy, Alice just measures, Bob measures if it's in this subspace or if it's in the 2 states, right? So it has these 2 outcome measurements. If he gets 2, then this part of the state is destroyed, and the post-measurement state is maximally mixed on Alice and 2 on Bob, right? In that case, it's fail, right? They destroy the entanglement, right? But suppose they get this outcome, 0 plus 1, then, right, these are orthogonal to this part, so this part doesn't appear anymore, and they have a perfectly maximum entangled state, right? So they make a measurement, and what is the probability of making the measurement? Well, is half in each case, right? With probability half, they get a perfectly maximum entangled state. With probability half, they get trash, and then they just destroy it, right? They throw it away, right? So this says, right, that if you, for large n, this can be mapped to roughly, right? N over 2 copies, right, of phi plus, right? So that's a particularly easy distillation protocol because the state is so simple. There might be, sometimes the state is more complicated and the distillation protocol will be more involved, right? But that's the kind of idea, right, that you have in mind in distillation. Okay. So now let's just let's define a function, ed, of a bipartite state rho AB, and this will be what we call distillable entanglement is the best rate that we can get for transforming the state into EPR pairs. Right? So you can just define as the maximum over R such that there exists some quantum operations which are LOCC such that the limit when n goes to infinity that's equal to 0. Okay, so it's a little bit complicated to write, but the intuition is simple. So what we want to have? We want to have first a distillation protocol. So we want to have a sequence of LCC operations, lambda sub n, such that if you apply this to n copies of rho, we get a good approximation of n times r copies of EPR pairs. Okay, maybe just, this might not be an integer, but we can take the floor here, for example, right, if you want. And we want that the error gets arbitrarily small, so we want that in the limit this goes to 0, right? So it means that we are distilling well. And of course, if you can do that, it means that we can get nr copies of maximum entangled state in the end. Per copy of rho, we can get copies of the maximum entangled state. And now we want to see what is the best r we can get here. What is the maximum r which distillation still works, right? So if R is 0, of course, this always works, right? But that's not interesting. Then for very small r, this will work. But then, we keep increasing and it still work. At some point, if r is bigger than some threshold, there is no LCC protocol that can do distillation anymore, right? And we want exactly this threshold, this r. And this is called the distillable entanglement, right? So it's the best, it's a measure of entanglement now, right? So I was talking about quantifying entanglement before, so that's a way to do it. We just ask, how rho B compares in units, right? So to EPR pair, right? In this asymptotic regime. So this is sometimes called like, because we have many copies of the state, right? So asymptotic regime. And right, so for example, if we want to use the state for teleportation, that's the right figure of merit, right? K has distillable entanglement equals to K. It means that per copy of the state we can teleport K qubits, right? So that's one interpretation. Is the definition clear? But now you should look at this and be very scared, right? And with right, because this L, we don't even know a nice expression for it, right? Can involve this forth. We consider this on a large number of copies. We take right of the number of copies going to infinity, right? So this looks a very difficult thing to compute. And in general, is very difficult to compute. So for general rho B, mixed states rho B, we don't really have a handle. Okay, so we have some bounds, and we're going to see some bounds, and we have some protocols we can try, but in general, we cannot compute it. But there is an exception, and this is what I want to tell you. Which is for when the state is pure. Okay. So suppose you have a psi. Then in that case, there is a very simple expression for that, and it's just a function. We're going to study this now. It's called the von Neumann entropy of the reduced density matrix. Okay. We could also use rho B. So that's a nice result because, right, so this is a very complicated expression, and this is it's a very nice function, nice properties. So at least for right, it's a special case, it's bipartite pure states, but we have in that case we understand it really well. And therefore, in a justified way, this function, like the entropy of the reduced states, will be a good way to quantify entanglement for pure states. And this is indeed used a lot. And for example, to connect with what Burak is telling, and we're going to see this maybe tomorrow, we can study the behavior of entanglement in ground states, right, or in very low energy states of some local many-body model, right? And then we'll see that this function, which tells us about entanglement, right now we know why, right, because it's related to, is equal to the distillable entanglement. It has particular behavior there. For example, satisfy what we call an area law for entanglement, right? This function does scale with the volume, scales with the area of the region. And this allows us to use, this ansatz, for example, this tensor network ansatz that Burak is telling you about, right? So we all come together like at some point, but at the moment maybe is a bit disconnected, but yeah, just wait for it. Okay, so I haven't told you how to do it, but before let's now start studying this function, what it is. So as I told you, this entropy function of the reduced density matrix, right? And that's also a nice insight, right? Tells us that the amount of entanglement of a pure state is equivalent to the amount of mixedness of the marginal, right? And again, this only works for pure states, not in general, right? But therefore, we can just study entropies there now. So there are many choices for the entropy, but the one relevant here is this von Neumann entropy. was introduced by von Neumann a long time ago. So Shannon thought about this as well in the classical case. So it's equal, and of course it appears right in statistical mechanics that the definition, the entropy of rho is minus trace rho log rho. Okay, so rho is a density matrix. So again, we can take a function right of the density matrix by taking the function of the eigenvalues. So in particular, this is equal to but these are the eigenvalues of rho, right? Okay. So, so this quantifies how much entropy the quantum state has, and this is the same thing by this expression as the classical entropy of the eigenvalues, right? So, for example, for pure states, there should be no entropy there, so this function should be 0. Mixed states, they say proportional to the identity, it should be maximum, right? So, some properties of it. Let rho be a density matrix on a d-dimensional vector space, then is always bigger than 0, right? Just because this function minus lambda log lambda is always bigger than 0, right? So lambda is always smaller than 1, so minus log lambda is always bigger than 0. But it's also smaller than what is, if rho is the maximally mixed states, is this guy, right? Is proportional identity. What would be the value of the entropy? Who knows? Just compute this expression. What we get? Log d, right? So, and I tell you that's the maximum value. You can think why that's the case. So that's one property, right? It's between these two values. Here only for pure states. Here only for the maximum mixed state. Another property which is useful is that it's concave. So if you mix two density matrices, right, is an entropy, so it's a measure of disorder in the states, right? So it makes sense that if you mix, you can only increase the entropy, and that's indeed the case. It also satisfies a property that is called sub-additivity, and that for that one we have to consider a bipartite state, okay? And then the entropy of the bipartite state is always smaller than the entropy of rho A plus the entropy of rho B, the sum of its parts, okay? And we're not going to use this now, but it has an even stronger property. So this is sub-additivity, let's call it SA. And there's what we call a strong sub-additivity. That's now for the tripartite states, rho ABC, for example, and it is that the following. Which says right that the total entropy plus the entropy of the C subsystem is always smaller than the entropy of A with C plus the entropy of B with C. Okay. So why I'm telling this now? Well, this we're going to use now. Actually, this not yet, but we're going to use it soon. So let me. So because of this inequality, it follows the of course the right hand side minus the left hand side is always bigger than 0, right? So we can define a quantity, and this will be an important quantity for us. It's called mutant information. And it's just that thing, right? And we know it's always bigger or equal than 0, right? This is a measure of correlations between A and B, but not total correlations, quantum and classical. Okay, so you just measure total correlations between A and B. The same, for example, rho AB equals 0 if and only if rho AB is product. Okay, there is no correlations at all. And that's also, there is a quantitative version, but I'm going to tell you later, which is that's approximately 0. Also, you know, maybe I'll do like that. If and only if they say this close to product, and there is some quantitative relations, right? So we introduce it now because it follows directly, right? So we need, because of this inequality of von Neumann entropy, it makes sense to define this quantity, and quantity meaning is the amount of correlations between these two quantum systems, right? You can do the same thing for this expression, okay? So you can define an expression which is the right-hand side minus the left-hand side. That's called conditional mutant information. It's more subtle. It's also very interesting, but I will leave that for later because hopefully you have time to see an application of this, but I'm not sure. But yes. It is. Yes, actually, because you asked, that's the expression. The mutant information for some state rho is always bigger than half trace normal difference, right, of rho AB minus square, but in some context, but there's okay. Let me come here. Right, so let me so before, right, I'm going to show you how this works, and I will do that, but I want to tell you something more, because so why we're seeing that, we're looking at that to argue that just looking at the von Neumann entropy of the reduced density matrix, that's a good measure of entanglement, right? But now let me tell you also why, in a sense, that's the only measure of entanglement you should look for pure states, bipartite pure states, if you are in asymptotic limit of many, and by looking at just the reverse process. So let's look at entanglement dilution. Okay, so this is like not something you should try, right, in practice, but we can define, which is we start from some very good entangled states, maximum entangled states, and we just transform it into some noisy version of it. So let's put R here now. Okay. So we want to get n copies of rho AB, of some state rho, and we want to see what's the minimum R for which, starting from n R copies of maximum entangled states, we can do that, right? And then if you do the same expression as I wrote before, I don't want to do it, but the entanglement cost of rho AB is just now the minimum over R such that, right, we can do this transformation, okay? Such that we can by LOCC. It's the same thing from before. And then actually we can upgrade this result to the following. We already know the Distillation entanglement, right, is equal to the von Neumann entropy, but actually the entanglement cost as well is the same thing. So the two are the same, and they are equal to rho A. Okay. So that's what we call, like, in this setting, entanglement is reversible, right? So you know, we can start from some copies of maximum entangled states. We map into another number of copies of some arbitrary state. Well, for pure states, right? Some other pure states, but then we can go do the reverse process, and then we end up in the same number of copies that we started with, right? So let me write this. So you can start from some psi AB, n copies, right, for n big. You apply some LCC and you go to phi plus n times distillable entanglement, right, which is just S. Or maybe sometimes this is called entropy of entanglement, right? So let me use this notation. This is of entanglement. So you start from this times, right? So this is one of the statements, right? We can map n copies to this number. Then what we can do, we can now just do the reverse process, right? From here to here, but we can do any state we want. So we could also map it to some other state phi, okay? But now by the entanglement cost is equal to this function too, so we have n e psi over, right, e phi, okay? But it's reversible, so we can also go back from there to psi, well, you know, to first, we do entanglement distillation here now, and then we do that with n psi, and then we do entanglement dilution and get psi again. Okay, so we did all this transformation, so we can go back and forth. What is the point? We can go back and forth between psi and phi as long as the number of copies matches the amount of entanglement, right? So what this is saying is that n times e psi copies of psi, that's equivalent in the sense, right? If you have LOCC, that's the same thing as, is the same amount, the same resource as n e phi copies of phi. Okay, so what this means, it means that this quantity completely specifies entanglement, right? We don't need anything else, right? Because if you only know them, doesn't matter which state we have, we can map one to the other, right? As long, I mean, at least if we care about asymptotic transformations and very big, and we care about LOCC, right? Which is what we have been doing here so far. So, you know, whenever you talk about pure bipartite entangled state, there is a canonical answer, right? We should look at the von Neumann entropy, right? And this is what we will do. That's great. Sometimes, actually, for technical reasons, we have to look at some other entropies, like called Renyi entropies, and they are similar to these Chapter knobs that I introduced, but for entropies. But they don't have a nice meaning as von Neumann entropy, right? So this is the canonical way of doing that. So we won't have time to do that because I want to go to some applications, but we could ask exactly the same thing for mixed states, right? So the general question. And then in general, they are not the same anymore, right? So entanglement cost is strictly larger than distillable entanglement. We do not have an analytical expression like this for them. In general, we have no idea what they are. We can define just in terms of some complicated limits, like the definition, right? A little bit better for entanglement cost. And moreover, we have some interesting situation where for some states, the entanglement cost is always bigger than 0 for every entangled state, right, as it should be. But sometimes the distillable entanglement can be 0, okay? There are some states which are entangled, but you cannot extract pure state entanglement out of it. So they're called bound entangled states. There's a nice theory around them, some open questions too, but I will not go into that. But, you know, for mixed states, this is much more complicated, right? Also, you can ask the same question for multiparticle pure states, And again, it's a mess. Okay, we don't have an analytical expression for, suppose you want to distill maybe a G Z state, or you want to distill EPR pairs between all the parties, etc. We do not understand this, right? So it's a very particular case where we understand, which is this one, right? Which makes it worth knowing. Okay. Oh, the last 5 minutes, let me just, I will have time to prove the whole thing, but I just want to give you an idea on what the distillation protocol would look like, right? And then stop there. Yes. Yeah. Sorry? Well, we can do it formally, right? The same way we did for the syllable entanglement, but I didn't want to write it again. But indeed, it would be right. You take, sorry, the minimum right now. Yeah, right, because you want to, the most efficient, right? You want to use the least number of EPR pairs, right, to produce, right? So, right, so the formulation should be the minimum over R such that there exists a sequence of LCC protocols, lambda n, such that lambda n of minus this guy, the trace norm goes to 0, right? So, okay. Oh, no, oh yeah, right. What I wanted to write is dilution. Not distillation, yeah, maybe. Which is, yeah, this process called entanglement dilution sometimes. Is the yeah, entanglement cost. That's the name that it's given to it. Yeah, it means like what is the cost of constructing the entangled states, right? The cost in terms of EPR pairs. That's the reason for the name. Yep. Yeah. Okay. Well, actually, maybe how it was. How many? When should I stop?
3:30.
But I think Nathan's not here. There was something that I should leave some time for
So
question discussion. How you forward now?
finish 10 minutes early.
Okay,
That's
sure.
fine.
Yeah,
We have 10 minutes.
I see.
But if you find
No, it's fine. I can just yeah. I'll just say for.
need to fill those 10 minutes.
No, it's okay. Yeah. I just. Okay, so so let me tell you a little bit of the idea. So suppose you have this psi AB, and let's look at a 2-qubit state now. Okay. So a 2-qubit state. Remember, we have LCC, so we can do any local unitaries that we want, right? So in particular, we can always put the pure states in the Schmidt form, right? So let's assume it's in Schmidt form. So then that's nice. The state just have, we can write it as basically this form. Up to local unitaries, you can always do that. So it means, right, that we have many copies of it now. Where we just have the tensor power of this, right? And then we can write this as write this in this form, right? We just, I take the tensor power of this and I just expand it, right? The entanglement distillation is just to say what we call a projection into a type state, okay? So let's suppose the following protocols. Alice just measures the Hamming distance of her n particles. The Hamming distance is just the number of ones. And another way to say that is that Alice just measures the total spin in the z direction, right? So she just measures sum over I, sigma I z on the ith particle, but not the expectation measures, right? This has observed. This projects into one of its possible eigenspaces, right? So now suppose she measures Hamming distance on her particles and get outcome M. Okay, so she gets found that there is M1 states, right? Because you have this guy, right? Which is this, and then it's a kind of binomial expansion, right? So this is just the binomial expansion, where write this up here to the power of I, and this first term. Oh, you have tensor power. This is the tensor power, right, to the power of I, and then right. So it's the same expression as we have two numbers to the power. Yeah, of course. Yeah. Thanks. Yeah. Yeah. Sure. No, it's a tensor product. It's a tensor product of the quantum states, right? Maybe I didn't understand your question, but not a symmetric tensor product. No, it's just why I don't. It's not a tensor product in quantum mechanics. How you compose quantum systems is not.
Well, I will label the number of zeros at 0, 0 that you have, no, but somehow it can be distributed by.
Oh, I see. Sorry. Yeah, indeed. Yeah, that's right. They can. Let me see how to write this. Yeah. That's right. Yeah. So yeah, I wanna symmetrize them. Yeah, you're right. Right. So because they all appear with the same weights. That's the point, right? So you can just have, but let me see how to write this in the right way. So you want to have here the let me call this S and I, right? And what this does is exactly right. So just distribute this in all possible ways, right? So we have yeah, and then because of symmetrization, we won't have this, right? So this symmetrization does exactly that, right? So it's just a uniform superposition over putting 0, 0 in all possible positions they have there, right? Everything is super. Yeah, thanks. That's the way to do it. All right. So yeah, maybe I'll have to again last time because I got confused. Again, next class. But and maybe it's time to stop. But let me just say what we're going to do next time. We're going to see that once we make this measurement, Alice just measures the total sigma z on her half of the system. She will basically collapse in one of these guys. Okay. Right. So for a particular I, for like I equals m here. Entangled states. Remember last time we introduced maximal entangled state in every dimension, right? This is a maximal entangled state where the dimension is 2 to the power of m, right? If she gets outcome m here, right? E bits, right? So if she makes a measurement and she gets outcome m, E bits of entanglement, right? So now all we have to argue is that this m with very high probability is close to n times the entropy of the distribution lambda n1 minus lambda. Okay, and this will follow just from Beve's laws of large number. We are going to see it. So it's a very so because of the Schmidt decomposition, right? There is perfect correlations between Alice and Bob from the beginning. That's good. So all that this has to do in a way is to extract like perfectly randomness on her side, right? So she should get some uniform distribution, a bunch of possible outcomes on her side, and this will be, by the properties of the Schmidt decomposition, maximum right? And then you just have to argue that she can get the right rates, the Von entropy, and this will follow laws of large numbers. But let's see that in detail next time. So maybe here's a good point to stop. Thank you.
Just two announcements. So first, another thing is that, I mean, so this is a 1 hour and 20 minutes class. I saw that there are some people arriving 20 minutes late. You know, we put the starts at 2 in the afternoon so that you guys can drink beer late at night and still don't so try to make it fun because the door open all the time. I mean, you guys are all grown. I'm not going to tell you what. It's nice. It's just silence while the professor is speaking. Thank you. And so let's take a moment here. So they will for the.
Okay. Maybe I can take this out.